Hi, welcome back. Today we're going to take a look at our Chapter 4 test and preparing for that upcoming test. Just a couple of notes about how we use this particular video. You've been given a Chapter 4 review packet. You need to take that out. We're going to work through some examples that are in this packet, locate those, and follow along as I discuss these examples in the video, and it'll help you work them out. Use the examples that we've done and go back and answer the other questions that are similar to that in the packet. Before the test, you can watch the video again, go through those examples again, spend a little bit of time studying over them, making sure you just understand what's going on. And if you're having some questions about what's going on, make sure you're asking questions and maybe be prepared to ask any other questions tomorrow morning when you come in before the test. That said, we're going to go ahead and jump in. Here we see our first example. We're talking about drawing two cards from a deck of 52 cards. And I will add that we're not replacing the first one after we draw. We're going to draw one card, not put it back in the deck, and draw a second one. So the question is, what is the probability that the first card is the King of Hearts and the second card is the King of Spades? Now before we begin, there's one word in here that we need to make sure we note, and that is the word and. Wherever we see the word and in dealing with probabilities, that means that we're going to be multiplying probabilities of multiple events. So the first card is the King of Hearts, and that's what we need to find the probability of. The probability of a King of Hearts, if you know your deck of cards, there are 52 cards in it. They come in 4 groups: hearts, diamonds, clubs, and spades. Each card or each group of hearts or diamonds or spades, what have you, has 13 cards in it. They go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So every group has a king in it. So there are 4 kings in the deck of 52, but only one of them is the King of Hearts. So the probability of the King of Hearts would be 1 out of 52. That's the probability of a King of Hearts. Now we're going to want to take this, and when we have that word and in here, we're going to multiply it times the probability of the second event. Now the probability of the second event that we're talking about is the second card is the King of Spades. And now this is going to be the King of Spades, given that we've already drawn the King of Hearts. So the King of Hearts was drawn first. So after we take that first card out of the deck, there's not 52 cards there anymore. There's only 51. So we have 51 possible cards that we could draw. Now of those 50, and I just wrote 52 for some reason. The 51 cards that are there to draw, only one of them is the King of Spades. So we have 1 over 51 being the probability that there's a King of Spades, given that we already drew a King of Hearts. So what we have is 1 over 52 times 1 over 51. And real quickly, to remember to multiply fractions, we just multiply across the top and across the bottom. 1 times 1 is 1, and 52 times 51 is 2652. So our probability that we draw 2 cards, and the first one is the King of Hearts, and the second is the King of Spades, would be 1 over 2652, which is not very likely, but it is still possible. Looking at the second part here, we're asked what is the probability that the first card is the King of Diamonds, and, again we have that and the second card is a diamond. Just a brief note here, there are 13 diamonds, okay? We have 52 cards. There are 13 diamonds, and this is the diamond shape. I'll try and color it a little bit. I'm not an artist, but We have 13 diamonds. You also have 13 hearts, you have 13 spades, you have 13 clubs, but here we're talking about diamonds. The first card that we want to draw is the King of Diamonds. So we need to figure out that probability. We've already talked about the probability of the King of Diamonds being drawn first. And that was 1 over 52. Then we want to talk about the probability of the second card being a diamond. So we're going to multiply, since we have the word and here, we're going to multiply the probability that the second card is a diamond. I'm making a blue diamond here. I think that's a Lucky Charms, a Lucky Charms marshmallow. At any rate, we've got the second card being a diamond, given that first was the King of Diamonds. After I've drawn that King of Diamonds out, like we said before, there's only 51 cards in the deck. So this number on the bottom is going to be 51. There were 13 diamonds to begin with, but we drew one of those diamonds when we drew this King of Diamonds here first. So when we took that first card as the King of Diamonds out, how many diamonds would be left? That would be 12. So what we have for the second card to be a diamond, there are 12 diamonds out of the 51 remaining. So our probability that these two events are going to happen together would be 1 over 52 times 12 over 51. And that gives us 12 over 26, 52. Now 12 over 26, 52 simplifies, and that simplifies, I believe, to 1 over 221. 12 goes into both of those numbers, so we can simplify this down to 1 over 221. And that's the probability that you draw the King of Diamonds first, and that your second card is also a diamond. And we have another part down here, and that is, what is the probability that the first card is not a king, and the second card is also not a king? So again, we've got the word and in here telling us to multiply these things. We're going to do the probability of not a king. And again, there are 4 kings in the deck. There's a King of Hearts, King of Diamonds, King of Spades, King of Clubs, out of the 52. So the ones that are not kings, if there are 4 kings, there would be 48 that are not kings. So if we're trying to not draw a king, we've got 48 chances out of the 52 cards that are there. We're going to multiply this again because we've got the word and we've got the second card is also not a king. So the probability of second card not being a king, given that first card was not a king. So after, again, I've taken one card out that's not a king, there would be 51 cards left in the deck. The 4 kings are still in there. I took one out that was not a king. There were 48 cards not a king to begin with, so that would leave 47 cards that are not a king to be left for the second drawing. Now, again, we're going to multiply this across the top and across the bottom. And we multiply 48 times 47, that's 2256. And of course, 52 times 51 is 2652. Now we can simplify these. They both divide out by 12. And we can simplify this down to 188 over 221. And that would be your final probability for this situation. We're trying to draw a card that is not a king and then draw a second card that is not a king. Okay, let's look at another example. Following up, this is number 12 in the packet. There are 1,250 students at an elementary school. 50 children had their teeth checked by a dentist. Okay, this is 50 children out of the students, out of the whole school. That's they picked 50 out of that 1,250. And 10 of the children were found to have one or more cavities. So, the question we're being asked is, what is the probability that a student at the school has at least one cavity? So, this is what we call empirical probability. Empirical probability means it's based on our observations. Okay, and what we've observed is that out of 50 children, 10 were found to have the cavities. So we don't have anything to do with that 1,250 right here. We only know about these 50 children that we have observed. We call that a sample, and we've got 10 out of that sample that have at least one cavity. So we will say that our empirical probability will be, out of the 50 children, 10 had cavities. So the probability of a cavity at this school, we'll say, is equal to 10 out of 50. That, of course, simplifies to 1/5. If you want to put it in decimal, it would be 0.20 or 20%. Again, that's empirical probability. It's based on what we've seen. Now, part B asks us, how many children in the whole school would you expect to have at least one cavity? So no longer are we going to try to apply this just to the 50. We're going to try and apply what we've witnessed out of those 50 to the entire school. Well, based on what we've seen, we'd expect 1/5 or 20% of the 1,250 students to have them. Well, 1/5 of 1,250, of course, means multiply. So that would be 1/5 times 1,250 over 1. And using our skills of working with fractions, we multiply across, we get 1,250 over 5. And of course, we can simplify that. 1,250 divided by 5 would be what? 250. So out of the entire school, we would expect 250 students to have at least one cavity. And again, this is taking an empirical probability we got from a sample and trying to apply it to the entire population of the school. All right, let's look at the next example. Number 13. An urn contains 8 marbles. There are 3 blue marbles, 4 red marbles, and 1 white one. We've looked at this example set up a few different ways. Part A, if we draw 1 marble, what is the probability that it is blue or white? So here we're only drawing 1 marble. We have the word or in here, and the word or tells us to add probabilities. So what we're going to do is we're going to find the probability of a blue in one drawing, and we're going to add the probability of a white. Well, the probability of a blue, there were 3 blue marbles out of the 8 total, so that would be 3/8 plus there was 1 white out of the 8 marbles. That 1 white would be 1/8. So we simply just add these together, 3/8 plus 1/8. I noticed before some of you were having some issues with adding after we had multiplied several. Remember, when we add the fractions, the bottom number stays the same. We want the same denominator in both fractions, and we keep that denominator when we add. So we'll add the top numbers, 3 plus 1, and get 4. We'll keep the bottom denominator, and that'll be 8. So we have 4/8, which is 1/2. So we have 1/2 probability of drawing a blue or white marble when we draw out of this urn. Part B, we're going to draw two balls or 2 marbles without replacing the first one. Okay, this is important information. We're not putting the first one back. Or I guess guess I should have included the word without there. Without replacing the first one. What is the probability that the first one is going to be red, and, there's that word again, the second is white? Well, and is telling us to multiply. Remember, or tells us to add, and tells us to multiply the probabilities. So we're going to first off find the probability that the first one is red. The probability the first one is red, and then we're going to multiply that by the probability, again we're multiplying because it said and, the second one is white. Now remember, that's going to be given that the first one was red. So what I did was I pulled a red marble out, and now I'm looking at the probability of getting a white after that red one is gone. So the probability that the first one is red is going to be, let's see, there were 4 red out of the 8, so that would be 4 out of 8 times the second one being white, given that the first one was red. Now remember, when we took that first one out, we now have 7 marbles instead of 8. And there is only 1 white out of those 7, so we have 1/7. And we're just multiplying 4 eighths times 1/7. Again, multiplying fractions, we just go straight across the top and bottom. So our answer is going to be 4 over 56. Now 4 over 56 does simplify to be 1/14. So 1/14 is our probability that we will draw 2 marbles without replacing the first, and the first one being red and the second one being white. And we have one more down here to look at. And in this case, we're going to draw 2 balls without replacing the first one. What is the probability that one is red and the other is white? Now this sounds very similar to what we just did in part B. But what it is saying is that the order doesn't really matter. So what we're looking at is the probability that we get the first red and second white, or we could get the first white and the second red. So the order doesn't matter here. And because of that, we have 2 different scenarios. Remember, the word and tells us to multiply, but this word or here in the middle is going to tell us to add what we get when we multiply. So we're going to go ahead and start looking at these. We'll break them down. The probability the first was red, we said was 4 out of 8. And the probability the second was white was 1 out of 7. Remember, we didn't put that first one back. Then we've got or telling us to add. First white would be 1 out of 8. And the second red, we're going to multiply that, and second red would be 4 out of 7 this time, because there were only 7 left after we drew that white out. So what this gives us, when we multiply across, we get 4 over 56 plus, multiply across here, we get 4 out of 56. And sticking to your rules, you add the tops, you get 8, you keep the bottom, and we get 56. So we have 8 out of 56, and of course 8 out of 56 simplifies to be 1/7. So we have a 1/7 chance of getting a red and a white when we draw 2 balls from this urn. Okay, let's look at the next example. We have a couple more to go. In this example, a random sample of 100 adults were surveyed. They were asked if they regularly watched NFL football games. They were also asked if their favorite team had ever won the Super Bowl. The results are in the table below. Okay? Part A says, find the probability that the person's favorite team won the Super Bowl. So in this case, we're looking at all of the people, and we're going to identify the people whose team won the Super Bowl, which was this, out of all the people. So that would be 65 out of 100. See, we have this nice, this is called a two-way table. And it has two different variables that we're looking at. And we can compare them and group them based on whether those two variables are met or not in each case. So for the people whose favorite team won the Super Bowl, there were 65 out of 100. Part B asks us, what's the probability that we pick somebody out of the 100 that watches NFL games? So that regularly watches NFL games, that is. Well, we see out of all of those watched games, we had some that won the Super Bowl, some did not win the Super Bowl, but we had a total of 75 out of the 100 that watched games. So we got 75 out of 100, that simplifies to be 3/4. And I forgot to simplify this one up here. 65 out of 100 simplifies, I believe, to be 13/20. So the probability that somebody watches NFL games regularly would be 3/4. The probability that their team won the Super Bowl would be 13 out of 20. As we scroll down, we're asked to find the probability that someone watches NFL games given that their favorite team won the Super Bowl. So this is something we really need to be aware of here. When it says given that their favorite team won the Super Bowl, we're saying that we're only looking at people whose favorite team won the Super Bowl. So we are only looking in this column of people. We are not looking at anything outside of that. All of these other people have nothing to do with this problem. So, given that we're only looking at people whose favorite team won the Super Bowl, how many watch NFL games regularly? Well, first off, we have a total of 35 people that we're looking at, and watch games regularly would be 20 out of the 35. So that simplifies down to be 4 out of 7. So the probability that someone watches regularly, given that their favorite team has won the Super Bowl, is 4/7. Okay? And that's something that people get a little confused with sometimes when we read that given. And since it's written second, we sometimes forget that that's really the first thing we're looking at. Let's look at this next example down here. We want to find the probability that someone watches NFL games and their favorite team won the Super Bowl. So it has to be both of them. So we have, I'm sorry, I forgot what I was looking at. Watching NFL games and won the Super Bowl. Okay, so, well, we can see that all of these people watch games, and we can see that all of these people's team won the Super Bowl. And we're looking at all of the 100 people. So out of all of these, how many people had both their team won the Super Bowl and watching games regularly? So I think that would be this 20 right here out of the 100 total were the people that both watched games regularly and their team won the Super Bowl. So that was 20 out of 100. And of course that simplifies to be 1/5. Okay, so we've looked at some conditional probabilities there using a two-way table. Looking at this example, and I believe this is our last one, 15 students wish to select a subcommittee of 4 to talk to the principal about school improvements. We want to know in how many ways can this subcommittee be formed. So the first thing we want to ask ourselves is, does order matter? Does the order in which these items are going to be picked matter? Well, based on this, we're just forming a subcommittee of 4 to talk about school improvements. The order doesn't really matter because whoever's picked is going to be on the subcommittee no matter what. So since the order does not matter, we are going to be using a combination. And remember, we're talking about a combination of n items choosing r. That's going to be n factorial over n minus r factorial times r factorial. And in this case, n is the number of people we had to choose from, and that's 15. Okay, and then r would be the number selected, which would be 4 people. All right, and we're just going to plug these numbers into the formula real quickly. That's going to be 15 factorial divided by 15 minus 4 factorial times 4 factorial. That's going to be 15 factorial is 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And that'll take you a while to write out, but there you go. And 15 minus 4, of course, is 11 factorial. So that would be 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And of course, 4 factorial, I'm just going to write it over here, 4, 3, 2, and 1. Okay, so what we're going to do now is start canceling out some of these things. As we look, we can cancel out from 11 down to 1 in both groups. We have one of those on the top and the bottom, so we'll just cancel them out of the way. Over here, we have 4, 3, 2, 1 on bottom, and we have 15, 14, 13, 12. You can go ahead and multiply those out. Sometimes I'll look for extra things to cancel out. I see that 4 times 3 is 12, so we can cancel that. I can also cancel out this 2 and maybe make this 14 turn into a 7. So that would give me, and I'm running out of space here, let's see, I would have, let's see, I'll just come over here. 15 times 7 times 13 would give me what I get out of this whole problem, I guess. And that comes out to be 1365. So that means there's 1,365 ways to form this subcommittee of 4 people out of the 15 students that were there. Again, you don't necessarily have to cancel out all those things. You can multiply them out the long way. I just often look for shortcuts to do this. Looking at part B, if the subcommittee was to have a spokesperson, reporter, secretary, and representative, how many ways can they be selected now? Since we're looking at this and we're going to assign posts to the different people within the group, the order does matter. Okay, if you want to be the first person selected, you would be the spokesperson. Second person selected would be the reporter, and so on. So the order of selection does matter in this case, which means we're going to use a permutation. Now, permutation is very similar to combination. However, the formula works out slightly different. It's n factorial over n minus r factorial. Notice we're not using this extra r factorial down there. So in this case, n is still 15 and r is 4, so we're doing 15 permutation 4. That's going to give us 15 factorial over 15 minus 4 factorial, and you can probably see what's going to happen. I'm going to shorthand it a little bit. 15 times 14 times 13 times 12 times 11, 10, all the way down to 1. And you can see what's going to happen here. This becomes 11 factorial on the bottom. So this would be 11 times 10 times 9 all the way down to 1. And you can see, since I have 11 all the way down to 1 up here and 11 all the way down to 1 up here, or down there, these two cancel out. and we are left with 15 times 14 times 13 times 12. Well, when we multiply those out, we get 32,760. So we see that if the selection of, or the order of selection matters, we get it considerably more. We get 32,760 ways to pick them. When the order didn't matter, we only had 1,365 ways. So the order making a difference in the problem gives us a permutation, and the values of permutations tend to be much higher than those of combinations with the same values. Okay, that's it for our review right here, and hopefully you can take the rest of the problems in the packet and go through them with this experience of working out these examples we've done and get through them pretty easily. If you have any questions, I'll be circulating throughout the classroom, and if you go home and you're still studying and you have questions, please feel free to make note of those questions so when you come in the morning you can ask them before we get started on the test. Good luck on the test. Please take some time and make sure you're well prepared. I'll see you later.